Okay, this video is going to be about starting our programmer project. I'm still a little undecided on how much I'm going to really need this or develop this. I'm going to at least get a pick on here and at least get an Atmel chip on it, and seeing how things go from there, I'll kind of decide if I want to get into a full-blown sort of a product to end up with. It's really the only thing that makes sense if you do something that's got a lot of functionality to it. But we'll just have to see how it goes. So that's a little warning. You may be disappointed if you're into a programmer or whatnot. Hopefully you can get something out of this. There's a lot of serial communication protocols and things like that you can probably apply to projects that are totally different from a programmer. So hopefully this won't be too big of a loss. So we'll take a real quick look here at the flash memory programming specification for the 87XA family, and we'll be using this for our Bible for this project. And first thing we need to be aware of is that this document covers two different algorithms for programming the target depending on what the voltage that target runs at. And there's a 2 volt to 5.5 volt range and a 4.5 volt to 5.5 volt range. That's nominal 5 volts. So there's algorithm 1 and 2 and the voltage range to be aware of whenever you're reading any part of this document. Here this describes how to get into programming mode on your target chip. Here's some descriptions of ID locations and the memory map of your target. Different ones you might be programming have different sizes. Here's how to get into program verify mode. Also discusses low voltage ICSP mode. Here's your commands for communicating from the programmer to the target. All the things that the target can do. There's obviously a state machine built into these targets that read these commands and do their thing. And they're highly dependent on a specific sequence being followed. And that specific sequence depends on these flowcharts. Here's algorithm 1 for the low voltage. We're not interested in that one. Here's algorithm 2 for our 5 volt nominal. And basically this tells you the sequence you have to follow. First chip erase, then set the programming voltage, and then load commands. You want to load 8 commands. You're going to see in the code that we only send buffers of instructions that are modulo 8, and this is the reason why. You have to have do 8 loads at a time before you do the actual burn. And having the modulo 8 length on our data buffer, that means that the programmer has less to do. It doesn't have to calculate that the buffer might be short and you have to put in some padding. The padding's already done for us by the host code. Then you do the begin programming, and it's a timeout of a millisecond, and then you just determine if you're done or not, and then you verify. Actually, when I did this in assembly language on using a little 876 processor, I didn't bother doing the verify, but that I may or may not get that included on the next video when we actually burn the chip. Here's a flow chart for doing the configuration memory and the ID locations, and it's for our 5 volt nominal. Now this one's a little more complicated because it jumps around. The ID locations are a little bit separated from where the configuration word goes, but it's not too bad, and it's just a little bit just looks a little bit complicated. Here's our, I'll give you a little better look at it here. A little better than that. So there's basically the flow chart you follow. So we're going to be doing this. This is our goal, at least on the PIC for right now. And so let's go look at the code. And we've got some basic communication going, and we'll take a look at how we'll do that. Okay, let's take a look at the code that's going to run on the host. It's written in Python. We have some imports right here. They're pretty typical. Using sleep from the time module here for delays. Here the single class in this script is programmer GUI. We have some local variables to keep track of. Here's the commands that we send to the programmer itself, just single bytes. Arbitrary values start at 11 hex and go down to 1 dog hex. We expect ACK or NACK back from the programmer, and these are ACK and NACKs out of the ASCII table, 06 and 15. The init portion of this class just sets up the tkinter GUI. Here's a definition for all the radio buttons. Here's the definition to get the hex source file we're going to work with. On the status display, there's a one-line status display and the exit button on the GUI. And that's about it for the GUI. Init address. This sends the address of where we're going to start loading our target code at on the target PIC. So we send this address to the programmer, and it ensures that we're going to start programming it at that address. Init data length, that sets the length of the code block we're going to send. Now there's a maximum of 240 bytes right now. That's kind of left over from the 16F 876 version of this code, and that's going to expand. But right now it's 240 bytes max, and it can be less. So we have to send the data length so the programmer knows how much data is coming. Mod 8 bucket is modulo 8 bucket. It stands for. We're going to make sure the amount of data we send is modulo 8 in size, and that's due to requirements of the programming routine that Microchip has specified. Download data. This is where we send the actual data to the programmer. Request CRC. This is a request for the CRC when we download the data. Both the host and the programmer calculate the CRC on the data that's transferred. It's not the CRC in the hex file. This is just for this one block of code that's being downloaded. So here we ask for that back, and we check and see if it matches. If it doesn't match, we bail out of doing anything. Program target, it just sends a command to program the target with the loaded data, and we just sit back and wait for it to finish. Program CW is programming the configuration word for the PIC, the fuses in a lot of cases it's called. This isn't implemented on the programmer yet. Read prog, this reads the target data back. That's not implemented on the target yet. Request state. This is just some status, and this is kind of in flux how it's going to change. It's just a byte that comes back that has, right now it's supposed to have, if you're in high voltage mode, low voltage mode, and it has the status error bits from the serial communication, the USART error bits. and but that's probably not going to stay this way. Erase program. This erases the target's program memory. That's not implemented on the programmer yet. Erase data will erase the double EEPROM at the target, and that's not implemented on the programmer yet. Same thing with chip erase, nukes the whole target memory, program, EEPROM, and configuration word. That's not implemented yet. Send bucket. Now this actually sends the data, controls sending the program data over to the programmer, and it calls. We looked at these just a second ago: init data length, download data, request for the CRC, and then the program target command. So this kind of bundles everything all together. A function cell. This controls the decoding of which button we selected on the TK-Enter GUI. And right now we've got just a handful of commands in here. Run loop. This is kind of a hook. It's a radio button, run loop here. We run loop. You can put anything in here just for test purposes. Right now I have this thing called just transmit active in here, but it's totally debug. So this gives you the opportunity to put in some code and make it run from the GUI. Get hex. This reads the hex file. And oh no, this selects the hex file you're going to use on the GUI. It fills in a text line with your selection. It opens up the file reader, and you can select a hex file. Status is a status line on the GUI. Exit is the exit button on the GUI. Send command controls sending a command to the programmer, and I think right now only set address and set data length use this and fit this architecture. This might change and go away and need a more general purpose way to send information to the over the USART. Here's a receive ACK when we expect to get an ACK back. Everything's cool if we do. If we get an ACK, we set that status. I don't think anybody actually monitors the return value of this, however, but that'll change. Hex2int here turns hex from the hex file into integers, and it also calls toInt here. And I think this is going to all be replaced by either this ASCII byte .decode hex or integer a value and base indicate base 16 to get a base 16 value back. One thing, this is kind of odd if you're not familiar with Python. Everything in Python, just about everything, is an object. So it's ASCII byte that you read off of the hex file is an object. So it has a method, and one of those methods is decode. So you can see you can use your ASCII byte, whatever it's defined as, .decode, and here it says we want to decode it from hex. toInt, I just mentioned it's used by that function above. Parse hex is where we read the actual Intel hex file. So the first thing we do is read the file and get it into everything into this object called lines, and then for line and lines we read for one line at a time. We do all the following. Here we check for the colon, which is always the first, and we check for the last line. This is the record type. If it's the last line, it's a 1, and we quit. And the only other record type we're interested in is data, and that's a 0. Record type is part of the CRC calculation. This is the first time we've accessed anything that's part of the CRC, so we just set the CRC equal to record type. Now we look at the record length, turn that into an int, and that's part of the CRC calculation. Then we do some tests on record length to see if everything is kosher. Here we get the line address. It's part of the CRC. It's 2 bytes, so there's two. Each byte is added to the CRC. We do some tests on line address to make sure everything's what we expect and within bounds. Here we start the record of program data. So we read each byte of the record. First thing we do is put the two actually it's nibbles in the B2, and we calculate CRC on that, and we calculate the next pair of hex ASCII characters into B1. Now remember, we said that hex is the Intel file is big Indian, so we when we put those two bytes into the instructions, we flip them into little Indian by reordering them right here in the argument to bucket extend. We bumped the programmer counter by half of the record length. That's because record length is counting bytes, where the program counter is counting the 14-bit PIC instruction words. Here we compute the CRC and be sure if it matches the CRC at the end of the line. If it doesn't, we bail out. And here we test how close we are to the 240 byte limit of our instruction bucket. If we're going to have more room for 16 more bytes at least, we'll just loop back. If we have filled it up, we go ahead and send the bucket and then go back and do the next line. And then here's the just transmit, the one of the debug routine I was telling you about. Here's some notes for our communication values I've left in here. Here's some TK-Enter support. We import the TX file dialog. That helps us read our hex file in. Another thing is the icon. This is the icon. It's the folder icon that goes next to the hex selection window. And I have this note here: do not try to make this pretty. And that means don't take out any of these spaces. Don't move it up to this line. Don't do anything with this, or it won't load right. It just has to be exactly like this. So if you edit anything in here, your icon won't show up. And then this is a standard way to start the GUI. Just kind of just boilerplate for TK-Enter, and root main loop runs, and it runs the programmer GUI, which is our class, of course. You remember we set up at the top. So that's it for the Python code. Okay, let's take a look at our code for the programmer itself. This is written for the 18F 2550. Originally it's converted from assembly language code that was written for an 876. That helped out a little bit. This clock's running pretty fast on this machine, so this is about probably going to be equal to the machine code on the little chip as far as speed goes. I used MP Lab X 1.9. I'm still behind, sorry to say, on versions here, and it's the non-enhanced code because I think you need the C18 compiler, or I need to upgrade, one of the two. And this should be MX8 or XC8 rather compiler. So we've got some of our register definitions that we're going to use in the GPR. Our state byte, I've broken it out in the way the same way they break out bytes in the include files. So I just want to try out one of my own for the state bits. I'm still kind of in the frame of mind to OR in and mask out bits the way you do in assembly language. I've got to get out of that way of thinking when I'm writing C. Here's some other dudes that we're going to use to do various things. Our function prototypes. Last time I talked about prototypes, I said I got away with not having one in here, but I think somehow I was wrong, because it's turning out you do need all your function prototypes for every function. The configuration word is very different on this part, and there's like, I think it's 6 or 7 registers worth of configuration. So I started writing those out, did 2 of them, got tired right here, and just went ahead and figured out what all the pragmas should be. So this is every pragma line by line, and it's every bit is defined, whether it's whether I'm changing from the default or not. So just makes it go easy to go back in and change one of them if you decide to. Okay, our main is pretty straightforward. First thing to do is call sys init. Last time I talked about C code again. I mentioned you should probably use a hook into some other function, but I don't think that's necessary anymore. And this sys init works great just right here in main. The loop inside main is very simple. We wait to get a byte from the host, and then we decode it and do what it tells us to do. Pretty easy. It spends all its time waiting in this get UART byte. A get UART byte, this is a blocking function. That means it's going to stay there forever until a byte shows up. Really thinking about it, there's nothing else to do but wait for a byte. So this hasn't been a problem at all, and I don't think it's going to be a problem in the future. It's not really a lock that's going to block anything else going on. The trouble is, back on the host code we looked at, it's also blocking, but and that's not good, because the user will never get control back of the UART of the GUI, and you're gonna have to fix it. I'm gonna have to change that in the host code and make it so there's no blocking over there. I think it's okay here. System initialization. It came out to be a lot shorter than I figured it'd be, and all we're doing is setting up some ports in the RS-232, and this, however, doesn't set up any of the lines going to the target device, so those are going to be added in here. The interrupt, it's deceptively simple also. We just get a byte. It's the receive register causes the interrupt. So we go ahead and read the value from the receive register, put it in the variable RX byte, and we set the flag and state bits to 1. And that's it. Now the boilerplate for interrupt appears. I looked at the listing file. It looks like it's saving a bunch of stuff, but I don't recognize what it's saving. I'll have to look into that a little bit more. The interrupt here, from the documentation, this is supposed to be like a function where you can put in a type of interrupt, but that never did work. And I found this little note here explains that I found this on the forum on Microchip, and just use it plain old void interrupt, and it works okay, but I'm wondering if some of the types aren't possible, and I think the types help specify what you want saved during the interrupt. So I'm not sure if the W register is being saved or anything like that. I don't think the way it's hung up, like blocking in the get UART byte instruction function. Since that's blocking, there's nothing going on with any registers or anything that's going to really get damaged. So probably this is okay for this simple little interrupt system we have working here. Okay, here I've listed the commands that go back and forth. We receive from the host and go back the ACK and NAC. They're identical to the ones I pointed out in the Python host program. Decode command, after we receive our byte, it's just a simple case statement of looking at all these guys here for each case and do what it says. Here is the return state, where we just send the state byte back. Addressing it is where we receive the address. We don't do anything with it except store it right now. Here's where we get our data length. We store that for later use. Here's where we receive our receive program block function, and it makes use of the data length here to terminate this loop reading data. For this, we send an ACK for receiving the command. The host knows we're ready to receive. The data starts coming, we receive it, and we give them another ACK to tell them we finished. He'll ask for our, while we're receiving the data, we're computing the CRC all the time. And here's where the host asks us for that CRC and return that. And program target, this is where you would actually go out and burn the target chip, and that's not implemented, but we just send an ACK back. And that is basically everything. Here's commands. These are commands to the target. And here's here's the RSVP we looked at. That just sends our ACK or NAC or data byte back, however the case may be. Here's where you get UART byte, and here's where we block and just wait for data available to show up. When it does, we clear it right away and return. And after we return, the next instruction, then the next method was that decode, and that's it. Wait for the byte and decode it. That's the whole loop. And this delay here is not even called anywhere. And that's it for the code. Let's go see some of this, see what happens on the host when we send this stuff over here, and we'll check out that these two guys are actually talking to each other. Okay, now I'm going to try to show you what happens when what we got tries to talk to each other. Here's our little GUI, TK-Enter GUI. I'm having to shoot this off the video screen with the camera. I hate to do this. This machine is my development machine. It doesn't have FFmpeg installed, so I'm going to have to shoot it off the screen directly with the camera. So I hope you can see some of this. We open up our little GUI, and the first thing that's required, here's our little icon I pointed out. It's code you shouldn't mess with. We click on that guy, get a file scanner here, and we select a hex file, open that up, and now it'll accept all commands. You have to do this first before it'll do anything. I did that mainly because GUIs are annoying, and that's my bit of annoying thing to do here. So we continue on. We can get status for one thing and see if we're talking. and there's our status, and all we really get is a 1. This bit here is always a 1. It means the system's up and listening, and really none of these other bits are set at all. This is kind of a decode of the byte we get back from the programmer, so we know we're talking anyway. And the only other thing we can do is say burn this hex file and see what it does. And so a lot of this is debug statements. Every character we send across is printed out as we send it, just for debug purposes. You can see here first, maybe you can see it, we initialize the address to 0. We initialize the data length we talked about to FO hex. That's 240, or maximum buffer length. And then we send those bytes out. Remember, we computed a CRC on that data. We have 28E0, and we request that CRC back, and we got 28E0 is equal to 28E0. So we got back from the programmer the same CRC value, and then we told them to go ahead and program the target. Of course, it doesn't do anything except return this ACK, and that came back. Then the remainder of the file is another data length. This time it's 144 bytes. We send those 144 bytes across. Say our CRC was 1E47. We got back 1E47 equals 1E47. So we agree on the CRC. So we go ahead and tell them to program the target. Gets the ACK back, and then we automatically read the status back on this line, and we got the same status word. Of course, nothing's going to change. Oh, we had data available of 1. Oh, this is not reading the right data. Oh, that's there's something going on there. We should have got a 1, 0, 0. Well, there's a bug to work out. Have to do that for next time. So, okay, basically that's where we are so far. Thanks for watching. Hope you get something out of it. If you're not doing a programmer, maybe just the communication back and forth to help you out. Python's great to use, and really managing the USART on a little microcontroller is not that complicated. So anyway, next video is going to be about programming the target, and probably after that video, though, I'll be going on to something else. So thanks for watching. We'll see you later.